Seminar. My name is Anurag Shankar, and I will be talking about quantum computing. This is a talk that I gave. It was a 2-hour talk, and I condensed it into a 1-hour talk, and we'll see if I succeeded in doing so. It's probably also somewhat disorganized, but I decided to ascribe it to the Heisenberg's uncertainty principle for PowerPoint, which says that the slide position and its momentum, how fast I'll go through it, cannot be measured simultaneously. I'm not sure exactly what I just said. It sounds very quantum. So I guess we need to talk a little bit about quantum mechanics. I don't know how many people remember this, maybe from high school, or probably some physicists. Also, there are some physicists among us in RT. But quantum mechanics is known as the machine language of the universe. And so let me get into it just very briefly. To define classical versus quantum worlds, matter seems to behave very differently at the large and small scales. And these scales are referred to as classical and quantum. Classical and quantum mechanics are basically the study of movement of matter at these two scales under an influence of a force. And you might say, well, why is the movement thing relevant? Well, it's, for classical, it's very clear. It's Newton's laws and so forth. It tells you how spaceships get to their destinations and so forth. Quantum mechanics, explains how atomic and molecular subatomic particles actually behave under electric and magnetic fields. And so, like how electrons jump up and down, excited and de-excitations, and so the spectrum that we see, how molecules bind to each other and so forth. So that's what quantum mechanics studies. So the question arises, well, matter at small scales is made of matter at large scale is made of matter at small scale. So why are there different behaviors? Well, it turns out that the behavior on large scales is kind of the anomalous one. It's because the behavior at small scales is sort of the real truth, and then at large scales it gets washed out because of aggregation. But it's still there. So how did we learn that matter at small scales actually behaves differently? And this brings us back to the Double-Slit Experiment that you may recall from high school. And so I'm going to talk about a newer version of that experiment. It was actually originally done in 1801 by Thomas Young to refute Newton's corpuscular theory of light, that light is made of particles. He showed that that's not the case. So this is an interesting one because this was done in 74, I believe, and it's done with electrons. So you send a beam of electrons through a slit. This shows the arrangement here. And if electrons were classical particles, which means behaving like balls, then what would you expect? Well, you would expect something like that. So two slits, if you measure two slits where electrons are striking, what you actually see is an interference pattern. Interestingly, even if you send a single electron separated by minutes, you will still see the interference pattern. So this experiment was done in 1974. So, like, what's going on? Does the electron split or something? Well, we can do something. We can try to see what's going on. We can shine a light, figuratively speaking. When you do that, you can actually see the electron. You can tell which slit it's going through. But the curious thing that happens is the interference goes away. So if you try to actually observe the electron, then your interference is gone. So this shows the electron is definitely not acting like a ball. Of course, interference pattern proves that already, and then this gets even weirder it is. So what electron's actually doing is it's behaving like a probability wave. And that allows it to go through both slits and actually creates an interference pattern, just like files on the waves on a pond. So basically, the electron is everywhere at once. And where you see the fringes of the interference pattern, basically, all we know is the probability where it might be found. And as we have seen, observation actually affects the outcome. What it does, it forces the electron into its most probable location at the time of observation. Or in quantum lingo, the observation collapses the wave function, and that gets into the mathematical aspects of quantum mechanics that we need to go into. So that's basically what forces, that's what makes the interference pattern go away. So let's continue this further. Let's see if this is working. All right. So let's do a black and white sock and put them in a bag. These are regular socks that you wear. And now you close your eye and put a sock randomly. Open your eyes. Let's say that you pull the black one. Now you know for sure, deterministically, the other one's going to be definitely white. That's pretty obvious. Let's do the same thing again with little quantum socks. I'm not sure exactly where you would get them, but we're doing thought experiments. So let's do the same thing again. We pull one out. Let's just say it's black. So what do you think the color of the other one's going to be when you take it out? It turns out it will be either white or black. White 50% of the time and black 50% of the time. Well, you can't, but it's going to do it. It's going to do what it wants. There's no way that you can control it or predict what's going to happen, except 50%. This, interestingly, will happen even if you pull both socks at the same time. So you pull out both socks at the same time, there'll be some random combo. So you might ask, well, what's going on? What's the color of the sock? Why it's in the bag? It turns out the only way to describe it is that it's everything. It can be either, it could be both, it could be neither, or it could be all of them. It's basically we're not allowed to know what it is, why it's in there. So what this is known as is quantum superposition of two colors in this case, and we'll talk about states later on. Basically, the two quantum properties are superposed, they're intertwined. And when you observe, that's when it forces it, just like in the case of double-slit experiment, it forces it to be black and white with equal probability. So basically, what goes on in the bag remains in the bag. So you simply are not allowed to know what. It's a strange situation. Okay, I have heard of quantum entanglement. Things get even more strange. Let's take two quantum balls this time. Let's say one white and one black. Under certain conditions, you can do something which will cause their wave functions or waves to glom together. It's called entanglement. The property of entanglement is that if you observe them individually, you can actually see. So you observe one and you get black. If they're entangled, the other one will immediately turn white every time. If you entangle them again, and there's ways you do that, you observe the first one, it may now turn black because remember, it's the nature decides what the quantum property is going to emerge. So it'll turn out this is a critical thing in quantum computing. So if you talk about entanglement going further, you can take two entangled particles, keep one here, send one to Andromeda 2 light years away. And it turns out they will remain entangled. Weird. If you observe yours, you get black. The other one over there, Andromeda, will be white instantaneously. So this all sort of goes back to Einstein. He didn't like this all. He called all this stuff spooky action at a distance. It sounds much better in German, so we'll not try to pronounce that. What he actually believed, contrary to popular view, Einstein actually accepted quantum theory, in fact, as Nobel Prize. Photoelectric effect, used quantum theory to explain the photoelectric effect. He just didn't think that it was complete, theory was complete, that once it was complete, this probability stuff is going to go away and things will become deterministic again. In the early 80s, Alain Aspect, French guy, did the experiment and actually showed that quantum entanglement is actually real, it's not just a concept. So you say instantaneously. Well, how is that the knowledge of measurement is getting from here to there instantly? Doesn't that violate the speed of light? And the answer is it certainly seems to do that, but it's not a violation. It's because you are not communicating any information. And it's because you can't encode any information to begin with. Remember, your particles, you can't choose the color of the particles. You have to do that in order to encode it. Right? I mean, you have to know deterministically what the property is that you're sending. If the bit is 0 or 1. So you can't do that, then there's no communication. So that means there's no information being communicated, at least you're not doing it. So the question still remains, how does the other particle know? So we don't know. Just like in other cases, we don't know. But there have been experiments that actually show that over a distance of kilometers, and I think it's increased somewhat beyond that, tens of kilometers, that if there's a speed of action, it's at least 10,000 times the speed of light, which basically strongly indicates that the action is really truly instantaneous. So the speed of light is not coming into the equation. This is built into, like I say, the machine language of the universe thing. It's part of nature. So it really, is there a way to understand this in normal sort of human experience? And the answer is a big no. Interestingly, Richard Feynman, the great physicist, when he was teaching, someone asked him the same question. And he said, well, my students don't understand it because I don't understand it. No one understands it. So basically, let's just accept that nature is absurd because experiments show that these things actually exist. So let's accept nature as she is absurd. She allows us to do experiments and observe, but she hides what's actually going on in the back. Clearly non-intuitive for people as I call them, uncertainty challenged. We don't like uncertainty. And quantum mechanics is all uncertain. And yet, as I said, quantum mechanics is the most accurate and successful theory in all of physics. When experiments have been done and also calculations, the precision with which it can make predictions is absolutely astounding. So as Einstein didn't like this, but we accept the fact that God plays dice and go on. He said God does not play dice. All right, so how does all this apply to quantum computing? Well, first, classical computing, just to reiterate, all the computing that we know about is classical, like PowerPoint. It's deterministic, it leverages the classical behavior nature to compute. Again, started with mechanical devices, actually started with, computing as in using some sort of a mechanical device to compute would go back to Babbage, but of course people were computing on their fingers and stuff like that. So this goes way before that. In any case, all the electronics, tubes and all that, binary arithmetic is what we know. It's also not going to go anytime soon. And it's because, first of all, well, because quantum computers are not here and are probably going to be quite a while before they actually become truly practical and available. Secondly, they're extremely expensive. They will be for foreseeable future. And also they're not good at doing every single sort of problem, at least as they are today. And so classical computing is going to be with us. So just to go over briefly, very quickly over the history of quantum computing, all these famous scientists, Planck, Bohr, Einstein, these guys that developed quantum mechanics in the early part of the 20th century. Not much happened after that. In 1982, Richard Feynman actually introduced this idea, sort of stirred people's mind about possibly using quantum behavior of nature to compute. Things kind of happened a little faster then. David Deutsch proposed a quantum algorithm in '85. And then something really significant happened, which was Peter Shor developed a quantum algorithm for factoring large prime numbers. And then there was a quantum search algorithm that was discovered, or not discovered, but I guess Rover came up with it in '97. So basically, quantum mechanics was developed to handle this crisis in the late 19th century physics, because classical mechanics was not explaining a lot of stuff like spectra and things like that. So quantum mechanics came out of that. But there it stayed. Also, when you solve quantum mechanics equations, Schrödinger equation, it's very difficult to actually do something real practical with it for anything but the simplest of quantum systems, such as the hydrogen atom. So one single proton, for example, and an electron. So, but then we had classical computers, regular computers, and they allowed much more complex systems to be understood because you could solve these equations faster. But still, simulating quantum systems on classical computers is still pretty inefficient. So what Feynman did was at a conference, actually, he thought, well, maybe we can use quantum properties of nature to simulate quantum phenomena. And because we're using quantum physics, you can get tremendous speed up, and you'll see how. And so people worked on this some more, and it became clear fairly quickly that superposition and entanglement actually can be used in a practical way to get exponential quantum speed up over certain types of problems. In 1994, when this Shor's quantum algorithm for factoring large prime numbers came out, which is, by the way, the basis for all public encryption e-commerce that we have today. When this came out in '94, that concerned a lot of people, obviously, because for obvious reasons, e-commerce, I mean, it has a potential to disrupt everything that we have. Surely NSA was excited. They are still pretty excited. They were quite involved in all this. And I think it also, I would say, it marked the birth of the field of quantum computing proper, which means, well, I mean, you had algorithms and you started getting into the actual hardware. So we have had about 2.5 decades, and we have really, in some sense, a lot of progress, in other sense, not a lot of progress, but for good reason. It's very difficult. It's very difficult to actually implement these things in hardware. Okay, so let's get into the nuts and bolts. First, units of computing. You can always talk about the old way of doing things, the binary digit, only 0 and 1, 2 possibilities. And if you have n classical bits, it'll give you 2 to the n combination in 1 at a time. So if you have 2 bits, you get 4 combos, 0, 0, 0. So computing with classical bits is inherently serial, unless, obviously, like our big ret and all, you put lots and lots of
CPUs and do parallel computing. But if you had only just a single CPU, let's say, that's just going to be zero. Whereas quantum bit, which is also known as qubit, can be 0, 1, and can be anything in between. It can be anything in between, all infinity of different values you can assume. But when you measure it, then it becomes, again, just like with the socks and the balls, 0 or 1. So n qubits give you still only 2 to the n combinations, because when you measure, you're going back to the classical binary digit. But these 2 to the n combinations exist simultaneously. So all of them are sort of there at the same time. So if you can do something with that, now we're talking some serious speed up in computing. So basically, computing with quantum bits is inherently parallel. So again, we have 2 qubits here. You have certainly these combinations if you observe them, but you have, you have infinity of combos. I think there's actually, so in addition to qubits, which assume 2 states when measured, there's also this, you can generalize this. So there are things called qubits with three values, and then more commonly qubits, means it can have any number of values. So with, bits, bits are cheap. I got 64 gigabytes in here. That's 64 times 8 gigabits. But with 100 qubits, you can get that many combos. Well, same thing with bits, you get the same number of combos. With bits, but you're not going to get them in parallel, you get them all here. So that's a pretty big number with just 100 bits. In fact, you can just get tens of entangled qubits and to begin to get the benefit of quantum speed up. The problem is this all sounds good in principle, but in practice, you have to deal with hardware, and that's where the complexity comes in. As you increase the number of qubits, actually just implementing qubits is hard, and adding the number, increasing the number of qubits, as you can see, is extreme. So, in order to deal with these errors, practical quantum computers are going to have hundreds of thousands of qubits to actually overcome errors. We're nowhere close to that. We just started. So the way you do error correction often in classical computing is you basically make copies of bits. You've heard of RAID, for example, in disk arrays and all that. You store certain properties, parity and stuff like that. You can make, you can mirror disks and make copies of. In you cannot copy qubits. You can't do this in quantum mechanics for the very same reason, because copying means you have to have something that you can deterministically grab. You can't do that with qubits, so therefore you can't copy them. However, what you can do is you can spread them from one qubit to the other by entanglement, because once you entangle and observe it, then you know the other one's going to be a complement. So Shor actually also developed the first quantum error correction algorithm, same time as he came up with the other algorithm to disrupt e-commerce. That wasn't his intention. So the quantum error correction algorithm basically involves entangling a working qubit with other qubits, which are basically dedicated to that. They're called ancilla. But as I said before, doing quantum error correction means you need many more qubits than you need many more qubits. And therein lies the So let's look at the bit operations now. And I'll give you a simple circuit. Basically, it's a combination of 2 gates. It's a half adder circuit. Basically, it takes 2 single bits to input and gives a single sum and a carry. So it sums the 2 bits and gives you a carry. Let's do the quantum analog. You have 2 qubits, still 4 combos, but each qubit can take all the values simultaneously. So if you do the same sort of a half adder circuit, what's going to happen is you're going to have the input in superposition, you're going to get the output, which is the result, also in superposition. So in other words, you will get all the sums and all the carries simultaneously, at least on the output terminals, unless you mess with them. Because if you mess with them, then you pick one, whichever one is most probable at that point. All the rest are destroyed. So that's not very useful. Say. Indeed. You already said that. So then how do how do you do this thing? That makes it not particularly interesting. Well, it turns out that, of course, you can repeat the computation many times and let the most probable results emerge. This is not a big deal with quantum because we're talking very fast machine operations, and therefore you can do this. You don't do this with classical computing because there's no need, but in quantum you have to do this. In fact, there are algorithms that increase the probability of the right result, and actually they suppress the wrong ones until you get it to a value which gives you the most likely results, and therefore the result. And this is called amplitude amplification. So in classical computing, we say this bit is 0 or 1, on and off. That's in qubits. In the case of qubits, we don't say that. We basically say that the qubit is in a 0 or 1 state. And it's because the qubits are realized in different ways. And I'll talk about that in a minute. State is whatever property you choose to represent 0 and 1. For example, in classical bits, you have voltage on and off. To do something like that. But it could be anything else, could be left or right, black and white, up, down, whatever. Any property that gives you, at least in the case of qubits, two distinct. So if you read these kinds of quantum computing articles, you cannot escape seeing these things. This comes from actually quantum mechanics. This is called the Brock-Ket notation. You'll see the states represented by this 0 and 1 state kets. And so when you superpose these two states, then you have some amount of state 0 and some amount of state 1, and that's the combination. That's how it's mathematically represented. When you measure this, then you get to either 0 or 1 state. And the absolute square of alpha and beta actually give you the probability of the qubit being in that state. So when you entangle qubits, then they basically, as I said, they glom together. They cannot be, you can't tell them apart. So for 2 qubits, this state is represented as alpha 00 beta 11. It's also called Bell, EPR, Einstein, Podolsky, Rosen state, because these guys were the ones who were talking about these things way back when talking about entanglement. So entanglement really is a special kind of superposition where the two shared states requiring 2 qubits at a minimum. You actually need many more qubits in entanglement to do anything useful, but the other problem with entanglement is it's very ephemeral, as is true with qubits and all of quantum computing primitives. So they die very quickly if there's any kind of noise. So, but in order to do quantum computing, there's some essential ingredients like you need this salt and pepper. It doesn't taste good. So, same thing. You need the superposition of qubit states and entangle between 2 or more qubits. You can do some stuff with superposition alone, but not something that gives you a practical computer. It's more like experiments. That's where we are at, as a matter of fact. So the qubit states are superposed to input and output all the values simultaneously, as you saw in the slide I had earlier. Entanglement allows the qubits to be spread over to do error correction because there's a lot of errors. That's just the way things are. How do you create qubits in actual reality in hardware? As I said, you basically have to achieve two states somehow that are measurable. You can tell whether it's one or the other state. It have to be controllable, so you need to be able to control it. And they need to be stable, which they have to stay in that state for a while. And that while is 10 into the 100 microseconds at least. The problem is, again, as I said, noise is the problem, and its decoherence is basically means that the whole system falls apart. The decoherence. That's the formal term for it. It destroys entangled superposition and so computation as well. And this decoherence mostly comes from interaction with the environment. So you have some cosmic rays going through the equipment, or you have some radio waves, anything that can mess with this thing. And of course, keeping in mind that the quantum states are going to be naturally very, very tiny, because quantum behavior manifests itself only at the smallest scale. So it's also very susceptible to noise. So most of the dollars that people are spending on creating actual quantum computers are going into suppressing this noise. The rest of it is, okay, there are certain parts of it that might be expensive, but the noise is the killer. So as you can imagine, that's where most of the money is. So what quantum states can we actually use? Well, you can use photons. You can use polarization. Photons can be horizontally or vertically polarized. You can use the number of photons. You can use the time of arrival. You can use electron. Electrons, again, spin up or down. Occupancy, whether something has an electron or not, or excitation, whether it's in ground or an excited state. So you use nuclear states. You spin. There's a thing called optical lattices. There's atomic spin, but you get the idea. Electronics, Josephson junction, electronic Josephson junctions, which use charge, whether there's something has a charge or not, or direction of the current. So these are the quantum states which are currently, and there's something called quantum dot pair states. Get into the details, but you can sort of get an idea of these are the sorts of tools that you need in order to achieve any kind of quantum computing. I think I already mentioned the problems facing quantum computing. One is decoherence. Qubits die. They collapses them. Noise collapses them and corrupts them, and that basically stops your computation. That's kind of a problem, isn't it? Scalability, as I said, is a huge problem, because just huge problem in terms of creating many, many qubits and then entangling them, superposing them, all of those kinds of operations become very complex when you have more than few qubits. This is why most of the quantum computers we have today have very few qubits. Except one, I'll talk about that. And the third one is economics. And again, I didn't say that, but as you can imagine, the way to bring the noise down is to cool it down to pretty much zero. To do that, you have to have liquid helium, which requires a bunch of other stuff. You need to have some equipment to keep it cool. And that stuff does not come cheap. So these things are pretty expensive to build and operate. There are solutions, however. You can delay decoherence. As I said, one is by simply cooling. There's other ways of doing it where you can actually make these qubits live for minutes even. Quantum error correction I talked about. There's algorithms that actually can correct the errors by spreading the qubits and not affecting the main computation. Obviously, everyone is looking to find some way to implement this. So that perhaps if you could do this at room temperature, well, that would be amazing. And there's some people that are actually trying exactly that. So hardware. Here's some sexy quantum computers. Yeah, I look at my sexy iPhone 8 that I got 2 days ago, and then I look at these things. This looks like most of them look like the labs that I was in when I was a grad student in physics back many years ago. And that's basically what these things are. You see, the first one is a company called IonQ, folks from Duke and Maryland that have built something called an ion trap. So a few more words about that as an example of a quantum computer. You can use, as I mentioned, photons. You can use photon optical stuff. So that Delft in Netherlands, they use these things. IBM Q is a machine on which you can get an account, as a matter of fact, to play around. It's pretty amazing. And there, in fact, I think the one on the left looks kind of pretty. It's got all these, again, highly cool hardware to do this thing with. There's Berkeley Lab. Those guys are doing some things that just sort of give you an idea what these things look like. So the real quantum computers that we have, they use things like ion traps called Paul traps. And it's a physics thing. These are all hardcore physics stuff. Not quite down to engineering yet. Use NMR. This is stuff that you may have heard. NMR stuff is used actually in medical, and some of these computations are done on those exact machines in hospitals. Interesting. Quantum dots, diamonds, and diamonds have nitrogen, and the location could be vacant or not. These things can be used as qubits. The lattices, these are things where you have neutral atoms that are trapped. You can use them to make qubits. Intel inside. Actually, Intel is now involved with Delft, those guys in Netherlands, and they have some big $15 million collaboration to transfer some of that knowledge from academia into industry. And there's a company I think they have created, whose name I can't remember, but yeah, Intel's getting there, but not the Intel that we know and love. Yeah, it was just something. I was looking at cartoons on quantum computing. There's not a lot of them. The one that I found was just Dilbert. Dilbert had these cartoons. So just an example of what all you need to do. There's your ion trap quantum computer. So you have these calcium-43 ions, positively charged ions. You use a radio frequency electric field to trap them in a sapphire substrate. So you make them sort of, localize them in a very small volume. And in fact, there's a picture of those that use fluorescence and stuff to see them. Now you use lasers to cool the ions, microkelvins. So here you are not using liquid helium, but using lasers to take away energy, to cool them. Again, cool them. Remember, cooling temperature is just a measure of the motion. These things, so just basically lasers take away that motion. That's cooling. This actually gives them the occurrence times could be seconds, which is actually pretty good. This is probably one of the most promising architectures for at the moment. Then you use microwaves and laser pumping to put the ions in their excited state from the ground state, excited state. And then you use microwave pulses to actually fiddle with these qubits, do the operations, logic operations. And then you use optical pulses to generate this fluorescence to read the state. Obviously, we're not doing major computations with this thing. We're doing some very basic stuff. But they have actually achieved computations, simple computations like superposition and entanglement and few qubits. Sort of thing. There's also this system called D-Wave from Canada. And they are selling this. They have been selling these machines for quite a while, actually. Cost a lot of money. This is not a universal quantum computer. A universal computer is like our PCs that can be programmed to do anything. Okay, this is a computer that does only one kind of thing. They're basically finding minimums called optimization. Again, it uses something called quantum annealing, which is a way to minimize energy. They do that by using niobium wires and loops of niobium wire and cool down to liquid helium temperatures. They just released one in January, and they claim it has 2,000 qubits. And Google, NASA, and USRA company, they're actually collaborating to purchase these machines because they've been very, very controversial. A lot of people have used them, and they haven't found them to give any speed ups. And so whether they're doing anything quantum was questionable. I think it's been established now by independent researchers. There's some quantum stuff going on. Whether or not we're getting large speed ups on lots of problems is unclear. But it's promising that something is happening. Again, 2,000 qubits are all entangled, at least some of them entangled, and then you minimize the energy you program them. And I'll talk about how you program them, and then you minimize the energy, and the minimization, the way you program them, corresponds to the specific problem you're trying to solve. More recently, technology that has been developed by University of New South Wales in Australia have caused a lot of excitement. They actually have a 2-qubit system in silicon at room temperature, I believe, which obviously would be pretty exciting. They use electron spin to use as qubits, use radio pulses to create the spin for operations, logic operations. So if these guys can, there's a company that they formed, if these guys can actually get this thing to go, silicon is very cheap. If you can do it room temperature, you don't need all the liquid helium sort of crap. And radio is cheap too. You can do generate radio waves pretty easily. So this is an exciting development. So state of the art. So there's claims of 2,000 plus stable qubits on D wave. Whether or not that's exactly true is unclear. Outside of that, we're getting up to about 100 qubits in actual hardware. The biggest problem that has been solved so far is, at least in terms of arithmetic problem, math problem, is they have factored this prime number using Shor's algorithm, 291,311, just to get a sense of what the largest prime number is one which has 22 million digits in it. So we have some ways to go. So how do you compute, and how do you actually do the computation? Again, assuming universal quantum computer, not the D wave like quantum annealing, highly, something that does optimization, is you generate qubits, whatever your hardware, and you basically create an n-qubit quantum register. It's like classical bits. You put them in desired states. You perform operations on them. You actually create gates. That's basically how you do classical computing. You have all these NOT and all these gates. Create those in quantum computing as well. And you string them together to create these things called quantum circuits. And they're not circuits in terms of wires and all, but it's a sequence of operations that creates a circuit. And then you read the output states by techniques as like amplitude amplification, quantum search, the hardware things, fluorescence, and so forth. So quantum circuit is basically a sequence of operations acting on some small number of qubits, generally 1 to 3. So an operation may put two qubits into superposition, for example. They can entangle them and do some logic. And these are obviously needed to achieve a universal quantum computer. And so people are concentrating effort on that. Again, the problem is that because hardware is involved, what you can do in terms of gates is also limited by that hardware. You can only flip things so many times using RF and so forth. So, but still, amazingly, many quantum gates are actually achieved and are used that have names, normal names like controlled NOT gate. Some of these things are same as classical bits, but there's other ones called Hadamard gate, Toffoli gate, Fredkin gate, things like that. Here, for example, is a quantum adder circuit, and it involves a Toffoli gate, C0 gate, and that's what a quantum circuit looks like. It's a sequence of operations. Black dots, unchanged qubits. Vertical dots actually show entanglement, vertical lines show entanglement, and those the circled, the crossed circles are the gate controlled NOT operation. Here's a much more complicated circuit, which is a circuit for Shor's algorithm. And it's got Hadamard gates, a whole bunch of them. And there's some 90, 45, 90. Now, these are actually rotations. Certain operations that rotate spin, for example. And there's measurements, which shows up as a meter, which is pretty cool. As I said, hardware implementation of gates actually depends on the system used to achieve qubits. So, for example, if you're using spin qubits, then you may use laser optical pulses, tip the spin by some angle. Okay, and then that can represent a certain kind of operation. Controlled NOT gate has been implemented in silicon using strong magnetic field and voltage pulses, and I think this may be that silicon, the Australian folks, I'm not entirely certain. I know they have done certain gates. And the other problem, again, is these achieving qubits itself is hard. Keeping them stable is hard. And then keeping them stable long enough to do a gate is even harder to do. So ultimately, all this ends up being budget. How well you can, cool your stuff, how you can keep them separate. So, okay, how do you program these things? Already sort of get an idea of how you do that by these operations such as pulses, microwave pulses, radio waves, magnetic fields, and so forth. That's how you're doing programming. So in the particular sequence in which you are applying these things is a program. There isn't actually a high-level quantum language, like Java or C++, that can be used in any existing quantum hardware. However, there are syntactic versions of these languages. One probably most well known as QCL, and the other one is Lang. You can go. These are used to actually to implement algorithms, simulate calculations that you might do some. Here actually is an example of the QCL, part of the QCL for Shor's algorithm. It's interesting to read this because you see a whole bunch of int and all that normal things but then you come down here. Here's a Hadamard mix, which is working on these qubits. Then you have a Fourier transform, a certain kind of, it's also done in, it's a physics thing, really math thing. And you measure. Interesting. There's also quantum simulators. So you can actually use your normal languages to do simulations of quantum algorithms and circuits. And there's quite a few of them, as a matter of fact. There's a website that describes, has a list of these things. Go check that out. Quantum cybersecurity. I work at the cybersecurity organization, so I had to talk about that. Well, I mean, quantum computers will be susceptible, obviously, most importantly, to decoherence attacks. You flood the thing with radio waves, or you heat it up, or you do any of these things, and you've killed the computation. So you could have traditional attacks, for example, or you can have software attacks. And it's not that different, except just the mechanism, perhaps. But other aspects of cybersecurity, quantum-resistant crypto algorithms are being developed because of this concern with public key encryption stuff going. We're talking about the post-quantum world, post-quantum computing, post-quantum crypto world. So fortunately, there are a bunch of algorithms that are actually resistant to quantum cryptanalysis. QC will also allow generation of truly random numbers. Quantum mechanics gives rise to truly random things at the level of physics level. So you actually get true random numbers, which actually has quite serious consequences for cryptography and all that. You can do source code validation. Quantum cryptanalysis, obviously, again, because of the speed ups. So it has consequences for that. In fact, the D-Wave 2000Q that was just purchased by this company called Temporal Defense Systems is a cybersecurity firm, so they're doing something with it. Must be. Okay, apps. And I don't mean apps in the sense of apps on your phone, but quantum cybersecurity I talked about, quantum cryptography, quantum communication, quantum teleportation, quantum AI, and simulations. So quantum cryptography actually is a misnomer because there is absolutely no quantum algorithm used to encrypt. What's quantum being used for is to share a key, share just a regular key over a quantum channel so that the act of sharing not be thwarted. And once you have shared the key, then you do a normal encryption, normal symmetric encryption. So it obviously requires two separate channels, a quantum and a classical channel to do this with. Again, the idea here is the man-in-the-middle attack cannot occur because, well, at least we think that it cannot occur. It's because if you mess with it, messing with it means observing it, and that kills the whole thing. A couple of QKD protocols, just that you can look into. Quantum communication actually is a way to transmit 2 bits of classical information using a quantum channel using a single qubit. So this is a way to transmit more information than you can with classic. You can, for example, do well, twice as much. And if you have QDIT or something, you might be able to do a lot more than that. It's called super dense. Again, it's made possible by entanglement. This communication is limited by the speed of light. It's not entanglement. It's not the speed of entanglement or let's say the measurement. That's a different idea. Here you are actually doing something which is transmitting information by design, so it's limited by speed of light. Quantum teleportation. It's actually just simply the reverse of quantum communication. The transmitting quantum information through a classical channel. So you basically have an entangled pair of pre-shared qubits, and you essentially send the information from one to the other. And in doing so, your original qubit is destroyed. This has actually been demonstrated over quite long distances. I think from the mainland to Canary Islands or something like that, or I think over Canary Islands, hundreds of kilometers. Yeah. So they can't do this. In fact, the Chinese are trying to do this between ground and a satellite up in space. So this is not quite Star Trek style transportation, but because that's obviously comes up, I thought I'd say a word about it. So is human teleportation ever possible? Let's say what it would entail in the quantum sense. First of all, something will have to scan all 10 to the 29 atoms in your body. read their quantum state, and then teleport them to the remote teleporter. Okay, never mind the difficulty. And the remote teleporter will use this information and bag a bunch of assorted atoms that it has to recreate you. But the original you is destroyed. So the question is it you? Is it really you? Who knows? But there's an excellent video you should read. That's pretty cool. That guy explains it. But again, people think about these things, and experts believe that this is going to be darn near impossible. I wouldn't say impossible because nothing is hard to say. Hard to say that right now, but it's unlikely. Quantum AI just simply means using the optimization aspect of quantum computing to do all things that require quantum optimization, such as doing flight trajectories, FedEx delivery of packages, air traffic control, candidate molecules. These are things that require you to minimize, like in this case, energy minimization, all those other things. This is a sort of bread and butter of what people do today, just on regular computers, having quantum computers which can go zillions of times faster, make the stuff. I mean, who knows where this stuff is going. Big data and all that kind of stuff is a huge. I didn't talk about it, but there's a huge consequence for privacy and all in this, because you can take large amounts of data and do things with predict exactly what maybe you will do next moment. Who knows? Airfares for complicated trips, traveling salesman problem, and all that. So I think it's my last slide. A quantum computer can model any quantum system. Obviously, that was the whole premise of it. That's how the whole thing got started with Feynman thinking exactly this. So if you have this, you can begin to simulate things like nature. You can simulate quantum behavior of lots of particles, which you can't really do on the classical computers because it's too expensive computation. So you do that. You have the speed to do this. This has tremendous. This will have tremendous impact on pharma and things like drug discovery and stuff like that, because that's what it is. It's quantum chemistry. All the drug discovery stuff is taking molecules and attaching a protein to it and things like that. High temperature superconductors. There's a huge number of things that will affect. Most interesting thing to do is it'll allow us to essentially simulate worlds which we absolutely cannot even imagine. Weird stuff. So what's the future? Well, everyone is clamoring for more qubits, more stable qubits, qubits, and I was amazed to see that some group has actually achieved a qubit using a chip with 10 states. And just imagine 2 qubits, 10 states. You're not getting just 4 combos; you get 100 combos. And then if you get more, so they're already doing this. That's amazing. Chinese are talking about quantum networks. They think by 2050 we'll have those. Not sure exactly what that means, but there's this term quantum supremacy is heard. Is whoever gets this first is going to basically be the leader of the world, including Putin. I think Putin's doing this. He's into this. So who knows? I will end with my another Dilbert slide. I will make more comments on that. So. Well, it's 2 o'clock. I don't think there's probably too much time for questions, but if anyone, you can open it up just in case anyone has any questions. Hey, Jeff. Yeah, maybe there is. Who knows? Maybe a minute. Well, it's 2:01, so I think we'll